Simplification via trigonometric substitution. Good day, everyone. Today, we will be diving into a very useful technique in calculus and trigonometry called simplification via trigonometric substitution. To start, let's look at our introduction. In your previous lessons, you have encountered inverse trigonometric functions. You will notice that these functions often contain complex algebraic expressions within their arguments. Now, the challenge we face is that these specific types of algebraic structures can be incredibly difficult to simplify using the standard algebraic methods you are already familiar with, such as basic factoring or expansion. To resolve this issue, we use a method called trigonometric substitution. Essentially, this technique allows us to swap out a complicated algebraic term for a trigonometric one, making the expression much easier to handle. Over the next few slides, I will show you exactly how to choose the right substitution and the step-by-step process to simplify these expressions effectively. Introduction to trigonometric substitution. Now that we have established why trigonometric substitution is necessary to handle complex algebraic expressions, let's look at the general mechanism of how this process works. First, we begin by replacing an algebraic variable, which is most commonly x, with a trigonometric ratio, such as sine theta, cosine theta, or tangent theta. This effectively shifts the problem from the realm of algebra into the realm of trigonometry. Once this substitution is made, our next objective is to transform the resulting expression into a recognizable trigonometric identity. By doing this, we can condense a complicated expression into a much simpler, single trigonometric term. Finally, we apply what are known as cancellation properties. For instance, if we encounter the inverse sign of sine theta, these two functions essentially neutralize each other, simplifying the expression down to just theta. In the upcoming slides, we will discuss the most critical part of this process: how to analyze your expression to choose the correct trigonometric ratio for the substitution. Choosing the right substitution. Now that we have established the general concept of trigonometric substitution, the most critical step is knowing which substitution to apply. As you can see on this slide, the choice of substitution depends entirely on the algebraic structure of the expression you are trying to simplify. Our primary objective here is to use specific trigonometric identities to eliminate cumbersome square roots or to simplify complex fractions, which allows us to move toward the cancellation properties we discussed earlier. Let's look at the first set of common substitutions. Whenever you encounter an expression containing the square root of a squared constant, a minus x squared, or simply 1 minus x squared, you should substitute x with a sine theta or a cosine theta. The reason for this specific choice is to utilize the fundamental Pythagorean identity. Sine squared theta plus cosine squared theta equals 1. More specifically, we are using the rearranged form, 1 minus sine squared theta equals cosine squared theta. By doing this, we can transform the expression under the square root into a single squared term, effectively removing the radical and simplifying the expression. In the next slide, we will explore other common substitutions for different algebraic structures. Choosing the right substitution, continued. Now, let's continue our discussion on choosing the right substitution. In the previous slide, we looked at how to handle expressions involving a constant minus a variable. Now, let's look at two other common scenarios. First, if you encounter an algebraic expression containing the square root of a squared constant plus a squared variable, specifically, the square root of a squared a plus x squared, or a simpler form like 1 plus x squared, you should substitute x with a times tangent theta, or alternatively, a times cotangent theta. The reason we do this is to take advantage of the trigonometric identity, where 1 plus tangent squared theta equals secant squared theta, which allows us to simplify the expression and eliminate the square root. Secondly, if the expression is structured as the square root of x squared minus a squared, you should substitute x with a times secant theta or a times cosecant theta. This choice is driven by the identity, where secant squared theta minus 1 equals tangent squared theta. By recognizing these specific algebraic patterns, you can choose the substitution that most effectively simplifies the problem. Now that we have covered the common substitutions, let's move forward to the step-by-step process of how to apply these in a real simplification problem. Step-by-step process for simplification. Now that we have discussed how to choose the correct substitution based on the algebraic structure, let us walk through the systematic process of simplifying an inverse trigonometric expression. I will break this down into a clear, step-by-step workflow. Starting with step 1, analyze the expression to determine the appropriate substitution. This is where you apply the guide we just covered in the previous slides. You need to look for specific patterns, such as a square root of a constant minus x squared, to decide whether you should use sine, tangent, or secant. Once you have identified the correct pattern, we move to step 2, perform the substitution. This means you actually replace the algebraic variable with a trigonometric ratio. For example, if your analysis in the first step suggested a sine substitution, you would let x equal sine theta. Finally, in step 3, you apply trigonometric identities to simplify the expression inside the inverse function. The objective here is to use those fundamental identities, like the Pythagorean identity or double-angle formulas, to collapse a complex algebraic expression into a single, simple trigonometric term. In the next slide, we will look at the final 2 steps to complete the simplification, and then apply this entire process to some concrete examples. Step-by-step process for simplification, continued. Moving forward to the final stages of our simplification process. Now that we have used trigonometric identities to simplify the inner expression, we proceed to step 4. Here, we apply the cancellation property. In mathematical terms, this is where the inverse function of a function of theta simply equals theta. Essentially, because the inverse function undoes the operation of the original function, they cancel each other out, leaving us with a much simpler expression. Once we have simplified the expression to a value involving theta, we move to step 5, which is to revert to the original variable. Remember, our goal is to simplify the expression in terms of x, not theta. Therefore, we replace theta with the corresponding inverse trigonometric function of x that we established during our initial substitution in step 2. With these 5 steps clearly defined, we now have a complete roadmap for simplification. To see exactly how this workflow functions in practice, let us move on to some detailed examples in the following slides. Detailed example 1. Now that we have covered the theoretical framework and the substitution guide, let's apply these concepts to a practical problem. Please look at example 1, where we are tasked with simplifying the inverse sign of 2x times the square root of 1 minus x squared. Before we dive into the math, it is worth noting that this specific type of simplification is not just an academic exercise. It is frequently used in physics and engineering, particularly when calculating phase shifts or analyzing circular motion. Let's begin with step 1, analyzing the expression. As you look at the argument inside the inverse sign, you will notice the presence of the term square root of 1 minus x squared. If you recall the substitution guide we discussed in slide 3, this specific algebraic structure tells us that the most effective substitution to use here is x equals sine theta. Moving to step 2, we perform the substitution. We let x equal sine theta. From this, it logically follows that theta equals the inverse sine of x. It is important to keep this second part in mind, as we will need it at the very end of our process to convert our final answer back from theta to x. Detailed example 1, continued. Now, let's continue with our first example. Having established in the previous slide that we will substitute x with sine theta, we can now plug this into our original expression. This transforms the expression into the inverse sine of 2 sine theta, multiplied by the square root of 1 minus sine theta squared. Moving on to step 3, our goal is to simplify the terms inside the inverse sine function using trigonometric identities. Recall the fundamental Pythagorean identity, which tells us that 1 minus sine theta squared is equal to cosine theta squared. Consequently, the square root of 1 minus sine theta squared simplifies simply to cosine theta. By substituting cosine theta back into our expression, the complex square root is eliminated. We are now left with the inverse sine of 2 sine theta cosine theta. This sets us up perfectly for the next step, where we will use a double angle identity to simplify this even further. Detailed example 1, continued. Now, let's pick up where we left off in our first example. From the previous slide, we had simplified the expression inside the inverse function to 2 sine theta cosine theta. To move forward, we apply a double angle identity. You will recall that 2 sine theta cosine theta is equivalent to the sine of 2 theta. By substituting this identity into our expression, the entire term simplifies to the inverse sine of the sine of 2 theta. Now we proceed to step 4, which is applying the cancellation property. Because the inverse sine and the sine functions are inverses of one another, they cancel each other out, leaving us with simply 2 theta. However, we cannot leave our answer in terms of theta. As the original problem was given in terms of x, this brings us to step 5, where we revert to the original variable. Since we established at the beginning of this example that x equals sine theta, it follows that theta equals the inverse sine of x. Therefore, 2 theta becomes 2 times the inverse sine of x. To conclude this example, the final simplified result is that the inverse sine of 2x times the square root of 1 minus x squared is equal to 2 times the inverse sine of x. Detailed example 2. Now that we have mastered the first example using sign substitution, let's move on to example 2. In this case, we are tasked with simplifying the inverse tangent of the quantity 2x divided by 1 minus x squared. Starting with step 1, we must analyze the structure of the expression. If you look closely at the fraction, you will notice that its form closely resembles the double angle identity for tangent. Because of this specific algebraic structure, the most effective substitution to use here is to let x equal tangent theta. Moving to step 2, we perform the actual substitution. By letting x equal tangent theta, it naturally follows that theta equals the inverse tangent of x. Now, let's substitute this value of x back into our original expression. By replacing every x with tangent theta, the expression transforms into the inverse tangent of 2 tangent theta, all divided by 1 minus tangent theta squared. In the next slide, we will apply a trigonometric identity to further simplify this result. Detailed example 2, continued. Now, continuing from where we left off in the previous slide, let us complete the simplification of our second example. Moving to step 3, we need to apply our trigonometric identities. If you look at the expression we just formed, you will recognize that it matches the double angle formula for tangent. Specifically, the tangent of 2 theta is equal to 2 times the tangent of theta, divided by the quantity of 1 minus the tangent of theta squared. By substituting this identity into our expression, the inner part simplifies significantly, leaving us with the inverse tangent of the tangent of 2 theta. Now we proceed to step 4, where we apply the cancellation property that we introduced at the beginning of this lesson. Since the inverse tangent and the tangent functions are inverses of one another, they effectively cancel each other out, leaving us with just 2 theta. Finally, in step 5, we must revert to our original variable. Recall from the start of this example that we substituted x for the tangent of theta, which implies that theta is equal to the inverse tangent of x. Therefore, our result of 2 theta becomes 2 times the inverse tangent of x. To conclude this example, the final simplified answer is that the inverse tangent of 2x divided by the quantity of 1 minus x squared is equal to 2 times the inverse tangent of x. While this process seems straightforward, it is crucial to be mindful of the constraints under which these simplifications are valid. In the next slide, we will discuss some common mistakes to avoid, particularly regarding the domain and principal value branches. Common mistakes to avoid. Now that we have walked through the step-by-step process and seen a few detailed examples, it is important to discuss some common pitfalls to avoid so that you don't lose marks on technicalities. First, let's talk about ignoring the domain. It is crucial to remember that the simplifications we perform are only valid within the principal value branches of the inverse trigonometric functions. For example, in our previous exercise, we simplified the inverse sine of sine 2 theta to simply 2 theta. However, this equality only holds true if 2 theta falls within the interval from negative pi over 2 to pi over 2. If the angle falls outside this range, the simplification becomes more complex. Secondly, be mindful of making the wrong substitution choice. As we saw in the earlier slides, the entire goal of this method is to use a specific identity to clear a square root or simplify a fraction. If you choose a substitution that doesn't align with the algebraic structure, for instance, using tangent when you should have used sine, you will likely make the expression more complicated rather than simpler. I strongly encourage you to refer back to the substitution guide we covered in slides 3 and 4 whenever you are unsure. Finally, a very frequent mistake is forgetting to revert to the original variable. Remember, the original problem is posed in terms of x, not theta. Theta is merely a tool we use to bridge the gap. Therefore, leaving your final answer as 2 theta is incomplete, you must convert it back to the original variable, such as 2 inverse sine of x, to provide a mathematically correct solution. Keep these 3 warnings in mind as we move toward our final summary and key takeaways. Key takeaways. To wrap up our lesson, let's go over the key takeaways on this final slide to ensure you have a clear roadmap for solving these problems. First, let's remind ourselves of the primary purpose of this technique. We use trigonometric substitution to convert complex algebraic expressions into trigonometric ones, which allows us to take advantage of cancellation properties to simplify the expression. Now, let's review the substitution guide, which serves as your cheat sheet for choosing the right approach. If you encounter an expression containing the square root of a squared minus x squared, you should substitute x as a sine theta. If you see the square root of a squared plus x squared, the appropriate substitution is x equals a tangent theta. And finally, if you are dealing with the square root of x squared minus a squared, you should use x equals a secant theta. To keep your work organized, always follow this specific workflow. Start by analyzing the expression to pick your substitution, perform the substitution, simplify the result using a trigonometric identity, apply the cancellation property, and, most importantly, as we discussed in the common mistakes slide, always revert the expression back to the original variable. Ultimately, your goal is to transform the argument inside the inverse function into a single trigonometric ratio of a multiple angle, similar to how we simplified our previous examples into sine of 2 theta. If you follow these steps, you'll be able to handle even the most complex inverse trigonometric simplifications with confidence.